Now let's go over to the final topic, composite functions. The definition of composite function is pretty simple. It's an extension of algebra functions like addition, subtraction, multiplication, and division, as you see over here. But it's a little bit different in that one of those important algebraic rules do not apply. It's not commutative. F circle G and G circle F are different. F of G of X and G of F of X are different. And then we already saw that kind of example right over here. In this example, F circle G and G circle F were different. Also, we did a computation how to find out a composite function. Excuse me. That's simply given by repeated application and working with parentheses. Now let's consider a little bit tougher example, getting a little bit warmer. Let's go backward. Given a complicated algebraic expression, let's express it as a composite function. How about the first problem? Y equals to 2x plus 5 over 4x squared minus 3. We can express this one as y equals x squared. G of x equals x squared will generate this x squared. And then the other is going to be this linear fractional map, 2x plus 5 over 4x minus 3. Then composing these two, we're going to get the original function that we wanted. So here in this expression, g of x is x squared, so this x will be replaced by x squared from here and there. Excuse me, I should have increased the font before doing that. Oops, too much. Okay, this x and that x should be replaced by x squared if I'm doing f of g of x, because g of x is x squared. And that's how we get this decomposition done. That was one example. How about the next example here? 1 over square root of that expression. Well, this whole expression that's this inside should be inner function. An outer function will be this 1 over square root function. Here it is. Outer function is 1 over square root of x. We have over there. And then inner function is going to be 3x to the 4th power plus 2x squared plus 1, like this over here. And then we have this kind of decomposition as an F circle G. Now, okay, that's enough. For some reason, if we're going to go a little bit further, then here's one such example. We have this thing inside, and then outside is squared. So an obvious decomposition is this. Outside function is f of t is t squared. Inside function is g of t is, well, whatever the inside parenthesis. And this u, which is this parenthesis squared, is given by f of g of t, or f circle g of t. But another way to do that is to get down to even further. G of t is this 2t minus 1 over 2t plus 1, which is a linear fractional map. It's relatively easy function to consider than this one. If I define like this, then we can decompose this original expression into the composition of 3 functions this time, because t squared, which is outside, is applied not only outside but here as well. So we have f circle g circle f again. And that's a little bit weird, but it's possible decomposition. In reality, decomposing like that is kind of rare. This kind of problem is rather straightforward. Whenever we have inside of denominator or radical or any kind of parenthesis, typical deal is that's inside function and outside expression is function of its own. And using that kind of idea, we can decompose any complicated expression as a composite function or composition of a number of functions which are simpler. Okay, getting warmer. How about this kind of example? We have to find out functions this time, but let's see. It's kind of functional equation, and we have to find out h and k of functions h and k, so that g of x is given by this one. This one is f of h of x, f circle h. Oh, it's hard to see. Let me increase the font again. So, okay. So the g, which is x plus 1, should be expressed as f circle h, and f is square root function. So this should be square root of h of x, basically. And how do we handle that? Well, here it is. G of x should be equal to f of h of x, and then if you have multiple parentheses, typically we do the inside first, but inside is unknown, h of x is unknown, so this time we have to take an exception, outside first, because inside is unknown. Outside function is a square root function, so f of x is square root. So square root of h of x is x plus 1, and now finding out h of x is not too bad. It's an equation, basically algebraic equation, square root of both, and we have h of x is x plus 1 total quantity squared, and that's the answer. You can expand it if you want to, but this complete square form is perfect. So sometimes you can set up a function equation, and find out a function. This one is gonna be still harder. F is equal to k of g of x. How's that? So here we go. K of g of x is f of x. So f of x is square root of x. No question about that. So we have this square root. Now k of g of x is f of x, and this time k is unknown, and g of x is x plus 1. So k of x plus 1 is square root of x. We have that equation. And k is not multiplication here, it's function k. So now it's not k times x plus 1. You cannot divide by x plus 1 here. What you need to do is to express the right hand side as an expression of x plus 1. Here we have square root of x, here we have x plus 1, and whatever inside of this function notation is absolute. You have to really express everything else according to that. So you have to express the right hand side in terms of x plus 1, which is x plus 1 minus 1. Now we are ready. Now that we have k of x plus 1 expressed like this, if we change this x plus 1 into x, then we are simply replacing this x plus 1 and consequently that x plus 1 by x. Here's the answer. K of x is square root of x minus 1. Basically, if square root of x minus 1 is k and g is x plus 1, and apply k of g, then you get original function back because you're just plugging x plus 1 in place of this x over here. So you get x plus 1 minus 1. Consequently, we get square root of x. Okay. I think I'd better just go ahead and do that. Okay, let's see. K of g of x is equal to k of g x plus 1, isn't it? And k, we did find out, and we are just checking that is square root of whatever inside we had minus 1. So if we simplify, we have square root of x, and is it what we want? Yes, that's right. So this is checking process. And once you know the answer, k is square root of x minus 1, this checking process is not too bad. It is just an algebraic expression of composite function. You can check that. But to do this in forward direction, finding out what k is, function k is from here in the second step is not easy at all. Okay, one more thing, and then let's go over to graph problems. Composing inverse function. If I compose inverse function, that's bringing back to the original value. So we start from x and then go to y by taking f, and then come back by f inverse, then we have to come back to the original place, and vice versa too. Inverse first and then go to y, and then forward direction, we'll go back to the original place. So inverse function and the original function will cancel each other out either way. We have been using this kind of things a lot. How do we kill off square root? By taking square. How do we kill off logarithm? By taking exponential. Things like those take place all the time. How much time do we have? Okay, so okay, oh, this isn't too bad. Composing inverse function. We have f of x is given by 1 minus square root of x plus logarithm of x plus 1, and find out f of f inverse of 1/2. Okay, this is a nice problem, and the latter problem is not really nice, because the first problem, f of f inverse of 1/2, you can answer this question even if you do not know what a logarithm is. It is just composition of the original function and the inverse function. So this f and f inverse part simply will cancel each other out, and we'll simply get 1/2. I don't have to do any computation with this expression. We have to simply get original one back. In this case, we really need work, so f inverse of 1 is b, so fb is equal to 1. And when do we have 1 in this expression? Well, there you go. I said clearly, but if you know the answer, it's clear, but it's rather ingenuous, I have to admit. How did he end up with x equals 0? Probably trial and error, I guess. So this whole thing is equal to 1 because we want 1, and then there's 1, so cancel this one and that one out, and then when we have everything just disappearing, and that's how we get x equals to 0, I think. But yeah, as I said, I don't like this problem very much. It's just too unnatural. This problem may look like a trick question, but it's not really a trick question, especially at this moment when you're just learning. Then inverse of an original canceling each other and simply getting the whatever we had here, 1/2 or whatever we had before, just coming back is so natural thing to do. Now, we do not have enough time, so let me just give you a preview of what's to come, and we're going to talk about it in the next session. And here we have graphs of f and g given as below, and graph of f is this red one, and graph of g is that V-shaped blue graph. And we have to answer the following question: f of g of 2, number 1, g of f of 1, c, those are inverse problems. We have to find out x values, and that's something we'll discuss in the next video. It is kind of similar to what we did way back in section 2.3 with something like this. But this time we had just one function. If we have two functions and consider composite function, that's harder, definitely. If you have 3, that's going to be even harder. But doing these kind of things with just 2 functions is definitely necessary, and we are going to discuss that in the next segment of the video.